There is a scar on the shoreline of Rombaksbotn in the far north of Norway. It is not a geological formation, it is a rusted, jagged structure of steel rising at a harsh angle against the dark rock of the fjord. From a distance, it resembles a fortification or a forgotten pier. When viewed from the air, the outline becomes unmistakable. It is the forward section of a warship, driven onto the stones with such violence that it still juts above the water more than 80 years later. This is the resting place of the German destroyer Z2 Georg Thiele. The Thiele is a paradox of naval engineering. She represents a specific moment in the 1930s when the demand for heavy firepower outpaced the understanding of hydrodynamics. She was a Type 1934 destroyer, commissioned in early 1937 at the Deutsche Werke shipyards in Kiel. On paper, she was a masterpiece of intimidation. She displaced 2,200 tons. She measured 390 feet from stem to stern. She carried a gun battery unusually heavy for a destroyer, designed to dominate the Baltic and the North Sea. But the physics of her hull contained a latent defect that would dictate her survival strategy in the narrow waters of Narvik. To understand why the Georg Thiele ended her life as a static battery on a rock, one must understand the concept of metacentric height. This is the governing value of maritime stability. It is the vertical distance between the center of gravity, which pulls the ship down, and the metacenter, the theoretical point around which the ship pivots when it heels over. A large metacentric height creates a stiff ship that snaps back toward upright after a roll. A smaller metacentric height makes a ship more tender, slower to recover, more willing to stay heeled, and it shrinks the margin between motion and danger. The Type 1934 design lived on a narrow stability margin. The engineers packed heavy guns, bulky directors, and a tall bridge onto a hull that left little room for error. In service, the class earned a reputation for being top-heavy and difficult in bad weather, and crews sometimes had to keep fuel low in the ship as ballast instead of burning it freely. In heavy seas, the Georg Thiele did not feel like a steady gun platform. She felt like a compromise. When she turned at speed, she could lean hard, her rail dipping toward the waterline, and every salvo had to be fought not just against the enemy, but against the ship's own motion. This flaw was not a secret. It was a known variable accepted by the Naval Command in exchange for raw speed and offensive power. They built a glass cannon, a ship with a devastating punch, but a fragile equilibrium. In the open ocean, this behavior was a liability. In the confined, calm waters of a Norwegian fjord, it became a calculated risk. The absence of heavy ocean swells masked the danger, allowing the captain to push the hull to its absolute limit. On April 13, 1940, the Georg Thiele was operating at that limit. She was trapped deep inside the fjord system near Narvik. She was not alone. She was one of several destroyers cornered by a superior British task force. The strategic situation had collapsed. The German force was low on fuel and ammunition. Escape to the open sea was impossible. The only tactical option remaining was to sell the ship as dearly as possible. The presence of the upright bow on the rocks today is not evidence of a navigational error. It is the physical signature of a deliberate choice. It proves that in the final moments, the ship was under command. It was not drifting. It was being driven. The destruction of the Georg Thiele was not an accident of war. It was a decision to trade the ship's mobility for a chance at survival, a choice that would later turn steel into foothold and water into escape route. The story begins with the engineering constraints that defined her life, but it ends with the sequence of decisions that defined her death. The steel standing in the fjord is the final receipt for that transaction. The fuel gauges on the German destroyers at Narvik told a story of strategic bankruptcy. The operation assumed that fuel support inside the fjords would be enough to turn a one-way dash into a round trip. In practice, the destroyers arrived already short of fuel, and the support plan narrowed to a single tanker, Jan Velem, with improvised gear that could only refuel a couple of ships at a time. Hours vanished at the hoses while ammunition vanished at the guns. The destroyers were still predators, but now they were tethered to the port by logistics. Fuel turned from advantage into constraint. In the open ocean, a destroyer survives by sprinting and turning hard, dictating range through speed. In the fjords, the Georg Thiele and her sister ships had to conserve every drop of heavy oil. They could not patrol effectively, and they could not run for the safety of the open sea. They were forced to wait in the dead end of the fjord for the British Navy to come to them. The situation was compounded by the mechanical heart of the ship. The Type 1934 class was powered by an ambitious, high-pressure steam propulsion plant. German engineers pushed for maximum power while minimizing weight, and to reach the design speed of 36 knots, they relied on Wagner boilers. These units ran on superheated steam at demanding pressures and temperatures to drive the turbines. High-pressure steam is a double-edged sword. When it works, it provides an incredible density of power, letting a destroyer of 2,200 tons accelerate with the aggression of a much smaller boat. But the system is intolerant of error. The intricate network of pipes and valves demands clean feed water and constant, precise adjustment. In peacetime, it takes specialists to keep it happy. In combat, it becomes temperamental, fragile, and perfectly timed to betray a crew. Contamination can steal pressure. Instability can slow the ship. Under stress, safety valves may lift, venting loud, violent plumes that turn confined spaces into chaos. Engineers can end up fighting for steam as hard as gunners fight for hits. The Georg Thiele was fighting two enemies. One was the approaching British fleet, the other was her own propulsion plant. This fragility dictated the mindset of the engineering team. They understood that a sudden demand for maximum power could collapse pressure at the exact moment it was needed most, so they nursed the plant, balancing violence against the limits of metal and water chemistry. It created a psychological pressure that matched the physical pressure in the steam drums. Down below the waterline, in a hot, loud steel box, they worked as if on a countdown. Because the moment the shafts stopped turning, the ship stopped being a warship and became a target. By morning, the trap had closed. The fuel bunkers were scraped dry. The surviving destroyers had retreated into the Rombaksbotn, the furthest reach of the water system. This was a cul-de-sac. The steep walls of the fjord rose on either side, blocking any lateral movement. The water was deep and dark. There was no room to maneuver in a traditional sense. The high-pressure steam system would not be asked to sustain a long voyage home. It would be asked for one final, desperate burst of energy. The captains knew that the British battleship HMS Warspite and 9 destroyers were pushing up the inlet. The strategy of evasion was over. The physics of the situation left only one remaining variable: how much damage they could inflict before the fuel and the luck ran out. The lethal physics of the boiler room were about to meet the external reality of heavy-caliber shellfire. The standard tactical doctrine for a destroyer division in retreat is predictable. The compromised vessels flee at maximum speed while laying a smokescreen to break the line of sight. The goal is to maximize the distance between the hull and the enemy guns. On the afternoon of April 13th, Captain Max Eckhart Wolff made a decision that inverted this logic. Instead of trying to outrun the trap, he took up a blocking position in the fjord and made a stand. This maneuver was an act of combat engineering. At the Narrows, the Georg Thiele fought alongside Z2 Hans Ludemann, buying time while other surviving German destroyers tried to reach the head of the fjord to scuttle themselves and get their crews ashore. If the British force pushed through the bottleneck, it could catch those ships before the men could escape. Wolfe used his ship as the stubborn edge of the defense, forcing the British to fight for every 100 yards of water. By turning broadside, he unmasked his full battery of 5 guns, presenting the maximum volume of fire while simultaneously presenting the largest possible target to the enemy. To make this stand effective, the gunnery officers had to solve the fire control solution. A predictive geometry worked in real time. One does not aim at where the enemy is. One aims at where the enemy will be when the shell arrives. The projectile takes seconds to travel. In that span, the target moves, the firing ship moves, and the wind steals small pieces of accuracy. In the Rombaksbotn, the variables were brutal. The Georg Thiele was maneuvering within rock walls. The range was closing fast. The British ships were no longer distant shapes, but distinct silhouettes rushing forward. The solution had to be updated constantly because a fraction of a degree in elevation was the difference between a hit on a British bridge structure or a splash in the cold water 400 yards beyond. The German gun crews worked the breeches of the 5-inch guns with a desperate rhythm. The ship vibrated with the recoil of each salvo. The noise in the fjord was amplified by the granite cliffs, creating a deafening echo chamber that made verbal communication difficult. The gunnery officer had to trust the optical rangefinders and the clockwork logic of the fire control table. They were trading space for time, using the violence of their own fire to force the British to hesitate. However, a destroyer is not a magazine of infinite depth. The Georg Thiele had been fighting for hours. The hoists that brought the shells up from the lower decks were running light. The ready-use lockers were empty. The reports coming to the bridge were grim. The rate of fire was unsustainable because the physical inventory of high-explosive shells was approaching zero. The fire control solution was accurate, but the variables were shifting. The equation was no longer about where to aim. It was about how many seconds of resistance remained before the click of a firing pin met an empty chamber. Wolfe held the position until the other destroyers signaled they were clear. He had bought them the necessary minutes, but the cost of that transaction was the safety of his own vessel. The British fire was finding its range. The water around the Thiele erupted with geysers from heavy shell splashes. The shield was cracking. The captain now had to transition from a static defense to a final kinetic attack. He had one card left to play, and it did not require a fire control computer to calculate. It required a straight line and a willingness to close the distance to point-blank range. The calculus of a destroyer duel at close range is a brutal economy. To secure a firing solution on a moving target, a captain must often expose his own vessel to a reciprocal line of fire. It is a trade where the currency is steel plate and human life. During the Second Battle of Narvik on April 13, 1940, the British destroyer Eskimo broke through the smoke and haze of the fjord, and Captain Wolfe accepted the trade. He committed the Georg Thiele to a head-on engagement, knowing that his ship was already critically compromised. The response from the British line was immediate and overwhelming. The Georg Thiele was hit repeatedly in rapid succession. The impacts tore through an unarmored hull and savaged the superstructure, wrecking control positions and ripping open systems the ship could not afford to lose. Steam and smoke turned passages into traps. The sophisticated aiming systems described in the gunnery manuals began to vanish, one station at a time. What remained was local control, where individual crews aimed over open sights, firing at silhouettes and muzzle flashes in the echoing fjord. Despite the carnage, the Thiele retained one final offensive capability. She still carried torpedoes in her deck tubes. In the hierarchy of naval weapons, the torpedo is the ultimate arbiter of terminal ballistics. A frantic exchange of gunfire might riddle a superstructure with holes, but the ship often remains afloat. A shell relies on kinetic penetration and a small bursting charge. It damages what it touches. A torpedo is different. It delivers its warhead below the waterline, and then the water itself becomes the weapon. When a torpedo detonates against a hull, the explosion creates a rapidly expanding bubble of gas. Because the surrounding water cannot be compressed like air, it acts as a solid hammer. It drives the shockwave directly into the ship's structure. This energy transfer does not just punch a hole, it shatters the keel and snaps frames. It creates a structural failure so catastrophic that the vessel ceases to act as a single rigid body. This is the physics of the kill shot. At close range, the Thiele launched one of her remaining torpedoes. The track was true. The weapon struck HMS Eskimo forward, and the detonation was decisive. The destroyer's bow was torn away, and in seconds, Eskimo went from a rushing predator to a crippled hulk, her forward buoyancy gutted, her motion brutally checked in the cold water. It was the kind of reversal naval combat occasionally permits. A ship already dying managed to cripple a healthy opponent. But the victory was Pyrrhic. The Georg Thiele was now a wreck. She was burning, taking on water, and her primary weapons were exhausted. The boiler pressure was falling. The duel had been won in a technical sense, as the enemy had been removed from the fight, but the Georg Thiele could no longer function as a warship. She was drifting toward the shoreline, a collection of broken compartments and failing systems. The captain looked at the smoking ruin of his command and recognized that the mission had shifted. The objective was no longer to fight. The objective was to ensure that the men who had survived the shell fire did not drown in the freezing water of the fjord. The physics of combat were finished. The geometry of survival was about to begin. For a captain in command of a sinking vessel, the confinement presents a binary choice. He can allow the ship to founder in the center of the waterway, dooming the crew to the freezing water, or he can use the shoreline itself as a tool of salvation. Captain Wolfe chose the shoreline. The maneuver he ordered is known as tactical grounding. In a civilian context, running a ship aground is a career-ending failure of navigation. In a salvage and damage control context, it is a deliberate conversion of kinetic energy into potential stability. A ship taking on water loses buoyancy, it sinks lower, eventually vanishing beneath the surface. By driving the hull onto a hard shelf at speed, the captain replaces the lost buoyancy with the physical support of the rock. He forces the ship to remain visible by pinning it against the land. This is not a gentle process. It requires the commitment of the final reserves of steam pressure. The Georg Thiele did not drift onto the rocks. She attacked them. The vessel accelerated, aiming for a flat slab of granite at the water's edge. The physics of the impact were violent. 2,000 tons of steel, traveling at combat speed, collided with the immovable geology of Norway. The force of the deceleration threw men off their feet, but it achieved the primary objective. The bow drove high up onto the shelf, biting into the rock and locking the vessel in place. The ship was no longer a floating object. It was a bridge between the hostile fjord and the safety of the land. However, the laws of structural engineering exacted a price for this stability. A ship is designed to float level, supported evenly along its entire length by the displacement of water. When the Georg Thiele struck the rocks, the bow was rigidly supported by the ground, but the stern was left hanging over the deep water. The hull became a massive cantilever beam. The weight of the aft section, loaded with machinery and flooding compartments, pulled downward with millions of pounds of force. The steel frame of a destroyer is built to resist the hogging and sagging of ocean waves, but it is not built to support its own weight in a suspension test. The hull girder reached its limit. With a groan of tearing metal, the wreck fractured amidships as the grounded forward section and the heavy, flooding aft section pulled in opposite directions. The bow remained stranded on the rocks, a permanent fixture. The stern section, no longer supported, slid backward and down. It did not stop at the surface. The aft section of the ship descended into the darkness of the fjord, coming to rest at about 170 feet, around 52 meters. This separation created the unique duality of the wreck site. Half of the ship was saved, serving as a platform for the crew to scramble ashore and escape into the mountains. The other half was sacrificed to the deep, taking with it the engines, the propellers, and the scars of the battle. The tactical grounding was a success because it traded the steel for the lives of the men. The ship was destroyed, but the crew was dry. To dive on the stern section of the Georg Thiele is to enter a time capsule sealed by pressure and darkness. Lying at a depth of about 170 feet, the aft hull can appear largely intact from the outside, but the condition of interior spaces is uncertain and may be dangerous. Diving here is not casual tourism. Currents, cold, and the possibility of unexploded ordnance demand local guidance, permission where required, and strict respect for the site. The stern is the private grave of the ship's mechanical identity, a silent counterpoint to the public monument that stands on the surface. The bow section, by contrast, is a part of the local geography. It is not a rumor, it is a rusted steel cliff that hikers can approach and touch. That accessibility, however, subjected the wreck to a different kind of violence. In the years after the war, parts of the Narvik wrecks were cleared and salvaged for practical reasons, and over time the most accessible, valuable fittings on the exposed sections were removed. Much of the accessible non-ferrous metal was stripped away over the decades, leaving the exposed steel to carry the full burden of time and salt water. Today, the primary antagonist of the Georg Thiele is not a British battleship or a salvage cutter. It is the slow, relentless process of galvanic corrosion. This is the electrochemical destruction of metal that occurs when different materials are submerged in an electrolyte like seawater. A warship is essentially a massive battery. It is constructed of steel plates, but it is fitted with bronze propellers, copper pipes, and brass valves. When these dissimilar metals are connected electrically in salt water, a current flows between them. The more noble metal, such as bronze, tends to corrode more slowly. The less noble metal, the structural steel, tends to sacrifice itself, corroding faster to feed the reaction. Over 80 years, this process can create a distinctive decay pattern. Rivets dissolve, plates thin, and strong frames turn to iron oxide. The Georg Thiele is slowly bleeding its structural integrity into the water of Rombaksbotn. Despite this molecular disintegration, the profile of the ship remains defiant. The tactical grounding that Captain Wolfe ordered in 1940 achieved a permanence that few warships ever claim. Most vessels lost in combat disappear, leaving only coordinates on a chart and a debris field on the bottom. The Thiele refused to vanish. By driving the ship onto the shelf, the crew converted their vessel into a fixed structure. The legacy of the Georg Thiele is not defined by the strategic failure of the Narvik campaign. It is defined by the successful execution of a partial salvage under fire. On April 13th, the mission was simple: get the human component out of the mechanical shell. That mission succeeded. The ship was spent like a coin to purchase the survival of the sailors. As the steel continues to rust and return to the mineral state from which it came, the logic of that decision remains watertight. In its final hour, the destroyer served its highest purpose as a lifeboat. And on the shoreline, the jagged iron still stands, proof that the captain chose lives over plating.